In this video, I will present a somewhat peculiar use of integration by parts. In the previous video, I have already explained the theory behind integration by parts, which is just the product rule backwards, and I work out some more straightforward examples, specifically these 4 examples. If you have not done so yet, I suggest you watch the video with these examples first. I'll put a link in the description. In this video, I will use integration by parts in a different way. I want to compute this integral. I invite you to pause the video, try to use integration by parts normally, decide whether it helps or not, and only after that, continue watching. I want to integrate e to the x times sine of x with respect to x. This is a product, so perhaps I can try to use integration by parts. And right off the bat, there is something suspicious. I'm trying to decide what I take as u, what I take as dv. Both the derivative and the antiderivative of e to the x are itself. And for sine, both the derivative and the antiderivative are plus or minus cosine. So whatever I choose, the transform integral is not going to be any easier. So perhaps integration by parts is not a good idea and won't help. Well, I don't know what else to try, so I'm going to try it anyway. Since I have no reason to prefer one choice over the other, I'll keep u as e to the x and dv as the rest. Then du is e to the x dx and v is minus cos x. Okay then, let's see what we get. Using integration by parts, I get u times v, that is minus e to the x cos x, minus the integral of v du, that is minus e to the x cos x dx. And just as I suspected, the new integral is not any easier than the original. So perhaps this is not leading anywhere. Well, I could try using integration by parts one more time. I don't see a reason why that would make a difference, but I'm already here. In for a penny, in for a pound. Let's see what happens. When I choose u and v now, I'm going to keep them the same. I'll take u as the exponential, and for dv I will use the trig function. Because if I swap them, I would effectively be undoing the integration by parts, and I would get a useless tautology. So u is e to the x, dv is the rest, then du is e to the x dx, and v is sine of x. Let's see what I get. I already had minus e to the x cos x, and now through integration by parts, I get u times v, that is e to the x sine x, minus the integral of v du, that is e to the x sine x dx. Oh, I got back the same integral I started with. Well, that's unfortunate. Perhaps this was all a waste of time. But maybe not. Let me give a name to the integral I'm trying to compute. I will call it I. Then this quantity at the end is also I. And it seems I've gotten an equation involving I. I equals this function minus I. I think I can use this equation to solve for I. 2i equals this function, so I is 1/2 of this function. So the integral I was looking for was 1/2 of e to the x times sine of x minus cosine of x plus an integration constant. Nice, isn't it? If you're skeptical, you can verify this result. You can take this function, compute its derivative, and you will get back e to the x sine x. In case you're wondering where this integration constant comes from, let's look at this equation here in red. I is not just a function, it's a family of antiderivatives. So it is a function plus an arbitrary constant. And on the right-hand side, I also have a function plus an arbitrary constant. But those two arbitrary constants may be off. They don't have to be the same, they don't cancel. So when I send both antiderivatives to the left-hand side, I still need to leave an arbitrary constant on the right-hand side.